Howdy. This video is on the concentration as a function of time. By monitoring the concentration of a reactant or product as a function of time, the order of the reaction can be determined. Knowing the relationship between the concentration and time, the concentration at a certain time can be determined, and the time to get to a certain concentration can be determined. After watching this video, you should be able to determine if reaction is first order or second order with respect to a reactant based on the concentration versus time. You should know and understand all the equations for a reaction that's first order. You should know and understand all the equations for a reaction that is second order, and you should be able to determine the concentration after a certain amount of time and how long it will take to get to that concentration. And so if we look at this reaction, it's first order because the exponent here is 1. And so we have rate equals K times the concentration. Now the rate is just a change in concentration over change in time. Now, if we're going to do a little calculus, now you're not required to understand the calculus. I'm just showing you so you know where the equation comes from. And so our delta becomes little d. And so we have the derivative of the concentration as a function of time equals minus K, the concentration. Now, if we multiply both sides by dt and divide both sides by the concentration, we get this. If we integrate it, we get that. And then we end up with the natural log of the concentration at time t. So that's what that subscript t means, minus the natural log of initial concentration. That's what that 0 means, equals minus kt. Now again, I'm showing you the math, but you don't need to memorize math. I just want you to know where the equations come from. And so this is the same equation that was on the bottom of the last slide. And so we can do a little algebra. So natural log of a minus natural log of b is that equal to natural log of a over b. So we get this. And now if we take everything to the power of e, we can get rid of that natural log. And then if we multiply it by the initial concentration, we get the concentration at time t equals the initial concentration times e to the minus kt. And so again, I'm showing you the math. Many of you won't understand the math, but that's fine. I just want you to have an idea where it comes from. And so we can also take this one and we can add natural log of initial concentration to get that. Now notice for this one, it's kind of important that it has the form of y equals mx plus b. And so if you plot the natural log of the concentration as a function of time, you should get a straight line with a slope of minus k. And so these equations are only for first order processes. And so if you combine all the equations I've talked about, we have, if you need to calculate the concentration at time t, you'd use this one. If you take this one, you can solve for t and determine how long it takes to get to a certain concentration. This one shows you that if you plot the natural log of the concentration versus time, you get a straight line with a slope of minus k. And so please note which equation to use for which situation. So again, if you're looking for the concentration at time t, if you're looking for the time, or if you want to remember that plotting natural log of the concentration versus time is a straight line, you'd use that bottom one. And so here's some simulations. And so this is the concentration as a function of time. It's a nice exponential. And here we plot the natural log of the concentration function of time, gives you a nice straight line. And again, the slope is equal to minus k. And so often, if you're trying to determine if a reaction is first order relative to the reactant, you'll look at the natural log of the concentration versus time, and if it's a straight line, then it is a first order reactant.
In a first order process, the rate of change of concentration of a substance is proportional to the concentration of the substance at that point in time. Suppose we begin with a unit concentration and follow the disappearance of the substance over time. We note that it takes 3.5 seconds for the concentration to reach 1/2 of the initial value. This time is called the half-life of the reaction. As the reaction proceeds, it takes another 3.5 seconds for the concentration to diminish to 1/4 of the initial concentration. Thus, this second half-life is the same length as the first. The third half-life is also 3.5 seconds long. In each successive half-life, the concentration of reactant drops to half that at the beginning of the half-life period. Notice that all half-lives are of the same length. The constancy of half-life is a distinguishing characteristic of a first-order reaction.
And so you'll see first-order processes in many places. All radioactive decays are first-order processes. And so the rate of the decay is proportional to the concentration. And for first-order processes, the time it takes to get to halfway is constant. And so if you start with initial concentration A0, to get to half that concentration takes 1 half-life. Now after here, another half-life, you'll get half as much and then half as much. And again, for first-order processes, the half-life is independent of the concentration. After 1 half-life, you'll have half as much, no matter how much you start with. So here we have natural log concentration time t over initial concentration equals minus kT. And so if we're looking for the half-life, and so we plug in a half for that fraction, label t our half-life, we get this. Now natural log of a half is minus 0.693. And so if we divide both sides by minus k, we get 0.693 over k is equal to the half-life. And so if you're given the k and you want the half-life, you just take 0.693 divided by the rate constant gives you the half-life. K is equal to 0.693 divided by the half-life. And so you can calculate the half-life from k and k given the half-life. So sucrose is fermented in a first order process using enzyme as a catalyst. The rate of disappearance of sucrose is equal to k times the concentration of sucrose. And so this is a first order process because this exponent is 1. And it gives you the k of 3.3 times 10 to the minus 4th. And so what is the half-life? And so we saw that the half-life is equal to 0.693 divided by k. And so 0.693 divided by 3.3 times 10 minus 4th per second. And that gives us a half-life of 2,100 seconds. And so if sucrose initial concentration is 0.01, how long will it take for the concentration to drop by 90% or to 0.001? And so there's a couple ways of thinking about it. We found that the half-life was 2,100 seconds. So after one half-life, you'll go from 0.01 to 0.005. After another half-life, you'll go to 0.0025. After the third half-life, you'll be to 0.0012. So we're getting really pretty close. And so our answer is going to be a little bit more than 6,300 seconds. Now we cannot determine it accurately, this method, if it's not an integer multiple of half-lives. We can determine that's going to be greater than 6,300 seconds, but using this method, we're not going to be able to do it exactly. And so what we have to do is we have to go back to one of the equations that we had derived. We saw that the natural log concentration at time t over initial concentration equals minus kT. And so we solve for t, we get t is equal to minus 1 over k natural log concentration time t over initial. And so our k was given as 3.3 times 10 minus 4th, and our initial concentration is 0.01. Concentration at time t is 0.001. If we plug this into our calculator, we get 7,000 seconds. And so we're right, that it is a little bit greater than 6,300 seconds, but because it wasn't an integer multiple of half-lives, we had to use this equation to calculate the time, and then we should get an accurate answer. And so again, please make sure you know the equations for first order process. And again, here if you're looking for how long it takes, here if you're looking for the concentration at time t, here if you want to remember that the natural log as a function of time gives you a straight line is the equation that you think about. And so I mentioned that all radioactive decays are first order processes and their half-lives vary greatly. And so uranium-238 has a half-life of 4.5 times 10 to the 9th years, while seaborgium has a half-life of 2.4 minutes. So if you have 1.5 milligrams of tritium, how much is left after 49.2 years? And its half-life is 12.3 years. And so again, if you think about the equations that we derived, you could do it that way. You can also notice that 49.2 years is equal to 4 half-lives. It's 4 times 12.3. And so after one half-life, you'll have 0.75 milligrams. After another half-life, 0.375. Another half-life, 0.188. And then after 4 half-lives, 0.094. And so here we have an integer multiple of half-lives. And so we can use this method. And we see that after 49.2 years, we should have 0.094 milligrams. But again, we can only use this method accurately when it's an integer multiple of half-lives. Now, if we want to use one of the equations that we derived, concentration at time t equals initial concentration e to minus kT. Now we can also just use mass here. And so our initial mass is 1.5 milligrams because the concentration and the mass are proportional. Our t is 49.2 years. Our half-life was given as 12.3 years. Now k is equal to 0.693 divided by the half-life. And so 0.693 divided by the half-life goes here. So the concentration at time t is equal to 1.5 milligrams times e to the minus kt. And again, k is 0.693 divided by 12.3 times t, which is 49.2. And we get 0.094 milligrams. And so for this case, because we had an integer multiple of half-lives, we can use either method to answer this question. And so again, if you're looking at concentration time t, we'd use this one. If we're looking for time, how long it gets, if we're looking for how long it takes to get to a certain concentration, we'd use this one. And again, this one shows us that natural log as a function of time gives us a straight line with a slope of minus k. Now if we look at this reaction, we're going 2NO2 to NO plus O2. Now our rate law is going to be equal to k times the reactants to some power, and that exponent has to be determined experimentally. Now if we notice, if we go from here to here, 0.1 to 0.2, so the concentration's doubling, the rate is going to be 4 times. And so 2 to what power equals 4? And so 2 squared equals 4. And so it tells us that this is second order. Now again, rate just means change in concentration over change in time equals k times concentration squared because this is second order. And again, if we want to be a little bit more exact, we change these deltas to d's. Now this gives us this equation. And if we multiply both sides by dt, divide both sides by the concentration squared, gives us that. And then if we integrate, we get that, and we get minus 1 of the concentration at time t plus 1 over initial concentration equals minus kt. And so these equations are only for a second order process. And again, I'm just showing you the math so you know where the equations come from, but you're not responsible for the math. Now if we take this equation on the next slide, and so we have that, and if we subtract 1 over the initial concentration, we get this. And if we multiply kt times the initial concentration, we can get that. And then if we flip both sides, we get the concentration at time t is equal to initial concentration divided by kt times the initial concentration plus 1. And again, I'm just showing you where these equations come from. You are not responsible for the math. Now, probably the most important equation for the second order process is this one, because it shows you that if you plot 1 over the concentration as a function of time, you'll get a straight line with a slope of k. And this one gives you the concentration as a function of time. So here's this concentration as a function of time. And here, 1 over the concentration as a function of time gives you a straight line. And so if you plot 1 over the concentration as a function of time and it's a straight line, it means it's a second order process. So just like if you plot the natural log of the concentration as a function of time, if that's a straight line, then it tells you that's a first order process. And so this is a way of determining if a reaction is second order relative to one of the reactants. For second order reactions, remember the concentration is squared, and we have concentration as a function of time here, and we have 1 over the concentration as a function of time gives us a straight line with a slope of k. Now if we want to calculate the half-life for a second order reaction, we can start with this equation, and then we solve for t. So we take this and we subtract 1 over initial concentration for both sides. Now we divide by k, it gives us that. Now if we're looking at the half-life, let's label t as t half. And so this means that our 1 over concentration at time t is going to be equal to 2 times 1 over initial concentration. And so we can simplify it and we can get that. Now, I do not like the idea of having a half-life for a second order process, because notice that the half-life for a second order process depends on the initial concentration, right? For a first order process, the half-life is independent of the concentration. So for a first order process, after one half-life, you'll have half as much no matter how much you start with. For a second order process, the half-life changes as the concentration changes. So I don't really like thinking about half-lives for a second order process. I don't think it's really that helpful. I think when we talk about half-lives, we really should only be talking about for first order processes, because the half-life is independent of the initial concentration. So the half-life for a second order reaction of substance is 50.5 seconds when the initial concentration is 0.84 molar. How much time is needed for the concentration of A to decrease 1/16 of its original value? And so first we need to determine the rate constant. And so K is equal to 1 over T half times our initial concentration. So we're given these numbers, and it gives us a rate constant of 0.0236 per second per molar. And so we can use the integrated second order rate law. So we have this. We can solve for T, gives us this. And then we plug in the K we just calculated, our concentration at time t, our initial concentration, and I get 760 seconds. So by looking at concentration as a function of time, we should be able to determine if a reaction is first order or second order. And so if the natural log of the concentration as a function of time is a straight line, it means it has to be first order. If 1 over the concentration as a function of time is a straight line, that means it has to be second order. For first order processes, we have one set of equations. And again, for first order processes, the half-life is independent of initial concentration, so the half-life is pretty meaningful. And again, you see first order processes in many situations. All radioactive decays are first order processes. For second order processes, this is the equation that you'd use, and it can be a little bit more complex. I hope that was helpful.